So when you're trying to determine if an infinite series converges or diverges, one of the biggest problems, I guess, that people face is which test should I use? So I'm going to kind of try to hit some highlights. Really, it's just a lot of practice, right? Just what you want to hear to know which one was best in which cases. So first off, you should always just start with a divergence test. Make sure that nth term, right, goes to 0. Right, so make sure that the limit, right, of that nth term is 0. Okay. If it's not 0, then stop. Your series diverges, right? Those terms, right, have to start getting smaller and smaller and smaller, or you're just going to keep getting bigger and bigger and bigger as you add. Okay, if the signs of the terms alternate, so if you either have a sine or a cosine that's changing the sign, right? So if you had like a sine n pi or a cosine n pi and then some other, right, term, right, or, right, a -1 raised to some power with your a sub n's, right? So that each term, each, right, successive term changes signs, right? Then you use the alternate series test. And for that one, remember, you just have to have that nth term going to 0, which, right, you've already checked from the divergence test. Okay. Now, if all of your terms are positive, okay, then we have, right, that's when the choices start coming in. So assuming that, right, we've passed the divergence test, it wasn't alternating because, right, if it passes the divergence test and it's alternating, then you've got it converging, right, done. Okay. So if we're going to fall into that, everybody's positive, right, then we have a set of tests that we can use. And there's, like 5 of them that we're going to talk about. So the first one here is a comparison test, sometimes called a direct comparison test. Okay. So what's powerful about this one is that you can decide, right, it works if the series converges or if it diverges, right? So you can show either one of those. There's just 2 of these tests that will actually help you show divergence. So if you think, right, if you think your series diverges, right, you can use this one. Actually, I guess there's a few more than that, but the way the comparison test works, right, is, right, so the 0, a sub n, b sub n, right, where, right, if we know that, and I'm not going to put all my other things. So if we know that b sub n converges and it's always bigger than a sub n, then we will also know then that a sub n converges. Okay. So for this one, right, a sub n is the one that you're given. You know something that's always bigger than it that converges, so something that you just know in your head. It's like, oh, I know this one will converge, so since it's always bigger, the one that I'm given, right, will converge. And then likewise, if, right, the smaller one diverges, then the bigger one will also diverge. So in this case, you're going to, right, this is if you think that the one you're given diverges, and you can think of something that's always smaller than it that also diverges, right, then, right, something bigger will also diverge because the terms are bigger, right? Each successive term is bigger. Okay, limit comparison. So this can only help us with converging. Okay, so, and this is where, right, you do that ratio. So you let L is going to be our ratio of successive terms. Right, and if, right, L is greater than 0, L is greater than 0, then a sub n, right, that series with a sub n converges if and only if the b sub n converges. Now, this is pretty powerful. Remember, if and only ifs, right? Those are awesome. So if either one of them will converge, right, then you know that the other one does. So, right, you're given your a sub n, right? If, right, there's a b sub n that you know converges, right, in this ratio, when you take the limit is greater than 0, so a positive number, then as long as, right, the one that you knew converged, right, the one that you were given will also converge. So if that limit is infinity, okay, now our statement is quite not as powerful, then a sub n converges, or I'm sorry, if a sub n converges, then b sub n converges. And if it equals 0, so we're just kind of doing all of the cases here. If it's 0 and, sorry, out of room, me and my spacing, b sub n converges, then a sub n converges. Okay, so you can see, right, this is only going to give us, the limit comparison will only help us show something converges. Okay. Let's see. So for the comparison and the limit comparison, you are going to have to come up with a series that you know something about to do the comparison. Okay, so what are some series you know stuff about? Well, the common ones, right? The ones that you're going to go to are going to be a p series. Okay, so the p series, so you have 1 over n, whatever your dummy variable is, and it's raised to a power. Okay, so it converges if p is greater than 1, and it diverges all other times less than or equal to 1. Okay, so, right, if we had 1 over n to the 1.2, this would converge because, right, the exponent, the power, is greater than 1. This series would converge. It gets small fast enough, right? Versus 1 over n to the 0.9. This would diverge because its power is less than or equal to 1. Okay. Geometric series. So remember, this is the common ratio. So you can have some constant or maybe not. And then r, right, is that constant ratio, and it has the power, right? And it converges if r is less than 1, and it diverges if r is greater than or equal to 1. Okay, so what would those look like? So you can have, right, a 5 maybe, and then if you had 2/3 to the n, this would converge because your r is 2/3, and that's less than 1. Okay. Versus, right, you can have 0.001 times 5/4 to the n. Okay. And this is going to diverge because, well, your ratio is greater than or equal to 1, and also, right, we're going to fail at the divergence test. My nth term is not going to 0. Okay. Now, the one that's kind of a tricky one, the harmonic series. So harmonic series is just, right, the p series with p equals 1. This series diverges. So even though, right, it's passing that divergence test, my nth term is definitely going to 0, but it's not getting there fast enough. So the harmonic series diverges, but the alternating harmonic series converges. Okay, because it would pass the alternating series test. Okay, so there's 4 tests. I have 3 more. Okay, so for the ratio test, this is super helpful if, right, I always use this one if I've got any kind of factorial. So use if you have factorials. Right, factorials are, right, the exclamation part. Because, right, what you're looking, again, it's another limit. So the limit, And now it's the absolute value of a sub n plus 1 over the absolute, or the a sub n term. Right? So you're just going to take that series that you have and you're going to write the formula with n plus 1 in place of all of the n's, and then divide that by, or usually multiply by the reciprocal of the term with just, that you're given, that generic a sub n term. You're going to do some algebra and you're going to take that limit for big n's, right? And then, three things can happen with L. So we'll let L equal whatever this limit is, right? If L is greater than 1, your series diverges. If it's less than 1, yay, it converges. If it equals 1, pick a new test. So it didn't give you any information. If it actually equals 1, if the ratio of the subsequent terms is 1, then it's not the ratio test. We say it's inconclusive. Okay, so you pick a different test. So you can use the ratio test for other things. It's just, if it's not a factorial or sometimes polynomials, you can do this. But if it's not one of those, quite often you're going to get this L equals 1 situation. And so then you just have to go do a different test anyway. Okay. Root test, well, where are you going to use that if you've got, so choose this one if you have something raised to an nth power. Right? So if your expression in here is all raised to an nth power, then this root test works really well. And the way we do this, it's another limit. So L equals the limit as n gets big. If we take the nth root, and we'll put it in absolute values just so we don't have to run into weird things. Nth root of the absolute value of that generic term. And then same situation as the ratio test. L is bigger than 1, it dives, less than 1 converges, and equals 1, pick a new test. Okay. And then finally is the integral test. And this is where you just integrate, so we have to let f of n equal a sub n. So we just take that generic nth term and make it a function. And then we're going to integrate it from some arbitrary value, to infinity, doing an improper integral. And the way we work it is if the integral converges, if the improper integral converges, then the series converges. And likewise, if the integral diverges, then the series diverges. So the thing about the integral test, you have to be able to find the antiderivative of your function. So if it's oh, I know the antiderivative of that, I'll go ahead and do the integral test then.